Hello everyone, this is Dr. E, and for today we're going to be working on how we think mathematically and analytically in geometry. In mathematics, we know that solving geometry problems, it's important that we know how to memorize formula and of course how to use those formula to be able to measure shapes, angles, lengths of our geometric figures. But in this lesson, what we're going to be working on is how to practice our analytical thinking skill and how we categorize them according to how we use this type of thinking in geometry. So we have three types of thinking that we're going to be using, and we're going to start with using logic to understand patterns. Because in mathematics, sometimes we just need to figure out a way on how the pattern works to be able to come up with a conclusion or understanding on how this pattern came to be. So let's look at this pattern in the list, and the list that we're going to be working on for this example will be 3, 4, 6, 9, 13, and 18. And our goal is to predict the next number after 18. And to be able to do that, we're going to be using logic to be able to come up with a specific or unique numerical value and operation that will help us complete this sequence of numbers. So our first term is 3. How do you think we went from 3 to 4 and from 4 to 6, 6 to 9 without using a mathematical formula but just using logic to think of that pattern? And in this particular case, let's observe how we got from 3 to 4. And the easiest way to figure out a way on how this increase is happening is we are adding 1 from the previous number to arrive to the next term. So from 3 to 4, we just simply add 3 and 1 so that we'll get to 4. Is this particular rule still applies from 4 to 6? So let's guess and check. If we add 1 to 4, 1 plus 4 is equal to 5, which is not 6. So perhaps we need to increase it by another unit. So let's try 2 this time and add it to 4 so that we can get 6. And in this case, it's still true. Now, by looking at the pattern, we are adding a certain number from our term or existing term, and in this case the pattern is seen to be an increasing number or numerical value from 1 and then 2, and then the next numerical value would be 3. So let's see if it's true for 6 to 9, and it seems like it because 6 plus 3 is equal to 9. So we are seeing a pattern based on our logical thinking. So that means from 9 through 13 we simply add 4 from 9 so we can get 13, which is true in this case. And that means we are now ready to figure out what or predict the number after 18 based on logic or logical thinking that we're able to show and formulate from this particular pattern. So from 13 to 18, we added 5 to get 18. So to get to the next number, we are simply adding 6 from 18 so that we can find the number after 18. And in this case, we know it's 24. So this particular way of reasoning and thinking is what we call as using logic to come up with ways on how to understand patterns based on this sequence. Now let's take a look at the second set of examples. So we have 3, 6, 18, 36, 108, and 216. Notice that the numerical values is a little bigger than the previous pattern, which means probably we are going to be using a different type of operation to complete this sequence. Because in mathematics, we have four common operators that we use, but we are not supposed to be limited by those operations because through the years, we know that we can also use exponents, we can also use fractions, we can also use roots as a type of operation for numerical values that we are getting in some math problems. But in this case, what operation do you think are we going to use to be able to find the number after 216? So we are seeing that from 3 to 6, 6 to 18, 18 to 36, we are seeing that we are multiplying a certain number. And I will start with 2. 3 times 2 is equal to 6. Now let's try 2 to get to 18. 6 times 2 is not equal to 18 but 12. But if we use 3 instead, 6 times 3 is 18. So is it going to be 18 times 4 this time? Seems like it's not the case. And if we subtract 1 again from 3, it's just 2. So we are seeing that the pattern is multiplying each term by 2, and then 3, and then 2, and then 3, and then 2. So that means from 216, going to the next number, we're going to multiply it with 3. That's why we got 648. Remember, there's no specific pattern for every numerical sequence, and we need to sometimes think of a way on how we'd be able to find that unique operation and unique numerical value that will fit the pattern, and using logic, we'll be able to do that. So that is the first method of reasoning that we can use in geometry and in mathematics so that we'll be able to think analytically in math. So the next one would be understanding the use of inductive reasoning, big word, inductive reasoning, to be able to understand numerical patterns. So inductive reasoning, by definition, is the process of arriving at a general conclusion based on observing patterns or observing specific examples, which seems like what we just did on the previous two examples is another type of inductive reasoning, because we're looking at the pattern and we arrive at a conclusion that to be able to go from first term to the second term, we're using operations to be able to come up with the correct numerical value. And that is what inductive reasoning is. Another example of inductive reasoning, let's say I'm traveling from Barstow to LA, and I've noticed that in a month or in 10 times that I travel or drive from Barstow to LA, it seems that it's always longer to travel to LA on a weekends due to traffic. So instead of driving from Barstow to LA for 2 hours, I travel sometimes at 3 or 4 when it's a weekend. So I can say that weekend, I will encounter traffic in LA, and that is another way of showing inductive reasoning because I'm looking at patterns, because I'm driving to LA every weekend. And I mean, not every weekend, but I travel to weekends, sometimes in the weekends, sometimes in the weekdays, and that's what I have noticed from the pattern. So, although inductive reasoning is a powerful method of drawing conclusions, we can never be absolutely certain that these conclusions are true. Which may happen because at one time I drove to LAX from Barstow on a weekend, and I've noticed that I was able to drive there pretty quickly, similar to when I drive there on a weekday. And I've noticed in the reason why I was able to drive to LA on a Sunday really quickly, even at 12 noon or afternoon, it's because it's a Super Bowl weekend. So there is a certain event that somehow made my conclusion or my pattern to not work as to how I predicted it. And in this particular case, we call it a conjecture. So in mathematics, for this reason, the conclusions are called conjectures or educated guesses because sometimes it's true, but at times it's not always true. So in that case, what I am making about traffic and driving on a weekend compared to weekdays is just a conjecture because it's not always true, but at times or most of the times it is true. And that is how inductive reasoning works and how we use these terms in mathematics so that we'll be able to understand it. When we are applying it or these terms in some theorems in geometry that we are working on, we'll be able to understand what it means. So let's take a look on how we use inductive reasoning to predict the next number in this particular pattern. So similar to what we just did from the previous two examples, but this time let's figure out a way on how to come up with a special pattern to go from 21 to this number that we are looking for. So let's observe it from 1, 1, 2, and 3. Now, it looks a little bit weird because if we add 1 or multiply 1 from 1 to 1, 2, and 3, something is still not quite right. But if we think harder, we are seeing a pattern that we started our pattern from 1 and 1 because 1 plus 1 is equal to 2 and 1 plus 2 is equal to 3. Would that be the case so that I will be able to find the number 21? So let's check. So 1 and 1, if we add 1 and 1, the first term and the second term, we'll get 2. And to get to 3, we add the previous two terms from 3, and 1 plus 2 is equal to 3. So that means if we're looking at number 5 right here, 2 plus 3 is actually 5. So we're seeing that the pattern seems to work in this particular examples that we have. So to go to 13, 5 plus 8 is equal to 13, which is still true. And 8 plus 13 is equal to 21, which means to get the number after 21, we can simply add 13 and 21, and it's equal to 34, and that would be the number that we are looking for based on the pattern that we are seeing. So this is how we use inductive reasoning, and our conjecture is we are adding the two previous terms of our sequence so that we'll be able to complete the pattern. So that is a conjecture because maybe we don't know, but for this particular examples, we know that numbers are infinite. It is true. And in this case, the number after 21 is 34 based on our conjecture. So let's see if you can figure out your own conjecture to figure out the number after 98. We have 23, 54, 95, and then 146, 117, and then, it went down to 98. Can you think of a pattern to be able to come up with this particular series or sequence of number so we can find the number after 98? I know most of you were able to figure that out, but this is how we are seeing the pattern from these numerical values. So 23 and 54, we're seeing that 2 plus 3 is equal to 5. 5 plus 4 is equal to 9. 9 plus 5 is equal to 14. And so on. So it seems that that pattern is showing us that all we need to do to go from 23 to 54 is to add 2 and 3, which is 5, and use the number after 3 or the succeeding number for the second digit. So from 23 to 54, we have 54 because 2 plus 3 is 5, and the number after 3 is 4. So that means from 54 to 95, 5 plus 4 is equal to 9, and the number after 4 is 5, that's why it is 95. And to go from 95 to 146, we know that 9 plus 5 is equal to 14, and the number after 5 is 6, which means if we have 98 right here, what we need to do is to simply add 9 and 8, and then the next digit would equal to 9 because that's the number after 8. And in this case, the number is 179 based on the inductive reasoning that we use to be able to come up with this pattern. So this way of thinking is called inductive reasoning because we are just basing our conjecture from the patterns that we are seeing in this sequence. And for the third type of reasoning that we need to work on is to form conjectures and finding counterexamples based on the patterns or statements that we are using in mathematics. So let's have an example on how we use this type of reasoning, which is providing counterexample, to prove that the conjecture is incorrect. So this is another type of thinking or reasoning in mathematics, thinking of a counterexample so that we can make or we can show that the conjecture that we have is false or incorrect. An example that I have given you, a counterexample, was the Super Bowl weekend. Because it's not all the time that the traffic is bad on a weekend driving from Barstow to LA, because during the Super Bowl weekend, the traffic is pretty mild and you can drive faster. So that is a counterexample. So in this case, our conjecture in this example is that the product of two numbers is always greater than either number. So that is our conjecture. To show you this conjecture, let's say we have 3 times 4. We know that 3 times 4 is equal to 12. And according to the conjecture, the two numbers is always greater than the number. Well, it's true for this specific example because 12 is greater than 4 and 12 is greater than 3, which is the 2-digit number that we multiplied to get to 12. And if we use it to 5 and 6, 5 times 6 is 30. 30 is greater than 5, and 30 is greater than 6, which is also true. But is it always true? So can you give a counterexample that will make that conjecture false? And my counterexample is negative 2 times 4, because negative 2 times 4 is negative 8, and we know that negative 8 is not greater than 4, and it's also not greater than negative 2, which means we are able to find a counterexample that will make the conjecture false. And I'm sure that you'll be able to figure out some numerical pairing that will disprove or make this conjecture false from your observation. So this is how we think in mathematics. So let's say all people in the USA are Americans as a conjecture. If you can think of a counterexample that will make this statement false, then you are understanding the term of formulating counterexamples to prove the conjecture is false. And in this particular example or conjecture, my counterexample is that Dr. E, who is me, is in the USA right now, but he's not American because he is still a Filipino and still a Filipino citizen. So not all people in the USA are Americans, because we can find counterexamples that some of them are still not American citizens, even though they're living in the United States. And this is how counterexample works, how conjecture works, and how inductive reasoning is working in geometric problems similar to what we have seen in our lesson. So our Numberbender challenge for today is, what do you think is the next pattern on this particular sequence of shapes and dots based on the way of thinking that you are using in mathematics? So this is how we think in not only in geometry, but mathematically, using logic, using inductive reasoning to be more specific. And we also learned how to use conjecture, what is conjecture, and counterexamples as a way on how we think or reason in mathematics. This is Dr. E, and see you again next time.